Thank you all for coming. Interesting invitation. So I'm going to be talking about a puzzle in theoretical physics that has troubled us for a long time. This is the black hole information paradox. And I want to start with a very brief history of this puzzle. If you heard about this from the newspaper headlines, you might know two things about it. The first is that nearly 40 years ago, Stephen Hawking argued that black holes destroy information in a way that's not consistent with the laws of quantum mechanics. It requires a modification of the laws of quantum mechanics. So that's the first thing you may know. And the second thing you may know is that in 2004 he changed his mind. Now, if that was the whole story, this wouldn't be much of a talk, but even after he changed his mind, even those of us who had agreed with him felt that we hadn't really answered his original arguments. There was still something not understood. And this has bubbled to the surface in the last year. Something else you may have seen in the papers. Namely, there's been a lot of discussion over the last year or two about an argument that preserving quantum mechanics actually requires a radical modification of Einstein's theory of gravity so that the interior of the black hole is very different from what Einstein's theory says. Now, the overall summary is that this paradox of Hawking's is one of the great thought experiments in the history of physics. Now, I see a lot of physicists in the audience, a lot of friends. So I understand that this is supposed to be a very broad audience. And so I want to say a bit about the role of thought experiments, how one can make progress in a field like this where data is so sparse, the unification of gravity and quantum mechanics, how thought experiments can be useful. And I actually want to go back to illustrate this with a much older thought experiment that goes back to the unification of electricity and magnetism. So here are Maxwell's equations, the laws of electricity and magnetism, and the four terms on the right were discovered individually at different times: Gauss's law, Ampere's law, Faraday's law, and Maxwell's displacement term. And the first three were discovered basically experimentally, and the last one, Maxwell's, was discovered via theoretical arguments, so that's the one I want to talk about. The equations before Maxwell, I blotted out the term that wasn't there. The equations before Maxwell actually aren't consistent. They don't make mathematical sense, and this one can reveal this in various ways, but a simple thought experiment in particular shows this. The thought experiment is just to take to have a current with a circuit with an oscillating current and a capacitor in the circuit. And if you take, and the experiment then is to measure the magnetic field at the x. And if you take Maxwell's equations before Maxwell without the last term, the equations don't make a consistent prediction for the magnetic field. You get different answers depending on how you solve them. And this can be fixed by adding that one additional term. Now, that wasn't Maxwell's only, this was not his only lever on the problem. I'll say a little bit at the very end of my talk about another way he thought about this problem. But this thought experiment reveals, again, the problem and with a little imagination also the solution. And of course, there was a great bonus, because when you combine Faraday's laws with Maxwell's new term, together they say Faraday's law says that an oscillating magnetic field produces an electric field. Maxwell's theory says an oscillating electric field produces a magnetic field. And so together you get propagating waves which travel with, in fact, the speed of light. And so the bonus for unifying electricity and magnetism was unexpectedly an understanding of the nature of light. Now, the point, though, is why, first of all, why was this discovered via a thought experiment and not a real experiment? So in order to see this term directly for the first time, it was necessary to reach basically the nanosecond time scale, circuits with a gigahertz resonant frequency. Hertz finally did this 25 years later, but you can imagine that that was a hard thing to do in the 1800s. And so that's why it wasn't discovered directly. So that's why a thought experiment was necessary, but why was it successful? And, well, you can kind of see, experiment had already provided 3 of the 4 terms. It wasn't that one was trying to discover the laws of nature from pure thought, but that one had a tremendous amount of information, and via theoretical argument, you can fill in the last puzzle pieces. The situation with quantum gravity may be similar. So the relevant time scale for that experiment was a nanosecond. The relevant time scale for quantum gravity, the time scale you get from dimensional analysis by combining Planck's constant, Newton's constant, and the speed of light, is basically a nano to the 5th seconds, 10 to the minus 44 seconds. So it's far beyond the reach of direct experiment, just as the nanosecond was in Maxwell's day. So we have the same problem, but we also have the same advantage because we have the theory of quantum mechanics. It is tremendously successful in its regime. We have the theory of general relativity. It's tremendously successful in its regime, and so one can imagine situations that could be realized in principle, if not in practice, and ask in these situations, what does quantum mechanics say? What does general relativity say? Are they consistent, or is there some mismatch that reveals the need for something new? So black holes. Now, there are several ways to represent a black hole depending on the audience, and I wasn't sure, so here are 2 of them. The one on the left emphasizes the space-time curvature. So gravity is the curvature of space-time, and Einstein's theory says that a sufficiently large mass will inevitably collapse, and as far as the theory can tell you, it will not stop collapsing until it becomes a perfect point of infinite density and infinite curvature. But before you get to the singularity, there's the horizon, the point of no return. Anything which gets past the horizon, even light, is doomed to fall into the singularity. Now, the singularity is obviously a place where quantum gravity seems to play a role because it's both very small, the realm of quantum mechanics, and also tremendously massive, the realm of general relativity. The surprise is that in thinking about how quantum mechanics applies in this situation, the horizon, which plays a remarkably central role. And that's surprising because the horizon, there's nothing special there. It's simply where the potential's gotten sort of so deep you can never get out, but it's a smooth, everything about the space seems smooth there. We sometimes say that this whole room could be falling into a black hole, and as you cross the horizon, you would not expect to see anything out of the ordinary, the laws of physics, and everything should be perfectly smooth, perfectly unchanged as you cross the horizon. So here's a more schematic representation that also shows the development in time. So, of course, just to emphasize, I've already lost the dimension here. The horizon is a sphere surrounding the black hole, but surrounding the singularity. Here I've lost the dimension further, so this whole picture is one, I've added time in. This whole picture is one time slice over here, and so you cross the horizon, the singular horizon again, that's here. But this also depicts the formation of the black hole, starting with some sort of diffuse matter. And by considering, again, quantum mechanics acting in this space-time, two related puzzles were uncovered. The entropy, and this is again going back 40 years or so, the entropy puzzle and the information paradox, which is what I'm mainly focused. Well, I'll talk about both of them. First the entropy puzzle. So these are two places where again the two theories give different pictures. In general relativity, the black hole is a smooth, featureless geometry. All black holes are the same. The slogan is "Black holes have no hair." Whereas quantum mechanics points to black holes having some kind of atomic, some kind of microstructure, some kind of substructure. And there are a couple arguments. One of them is, the first one is an information storage limit, and the second is the existence of thermodynamic properties. An old calculation of Bekenstein's is the following: is to simply ask how much information could you throw into a black hole, how much could it hold for a black hole of given mass. And so the relevant sort of variable here is the radius of the black hole. The various constants of nature are going along for the ride. But in particular, the minimum energy to add 1 bit to a black hole basically goes as 1 over the radius. That's because to fit inside the black hole, you've got to sort of squeeze it down. And the uncertainty principle then says there's some minimum energy. So it costs energy to add a bit to the black hole. Einstein's theory gives the mass of the black hole in terms of its radius. And so one can get an estimate of the number of bits of information that a black hole can contain by taking the total energy divided by the energy per bit. And you get an interesting number, which shows up in another close, very similar context. So Hawking showed, shortly after Bekenstein's argument, that black holes radiate with some temperature. And again, when you have a temperature, then kT is the basic unit of energy. And again, you can ask how many units of kT fit into the black hole mass. And it's the same number. And so again, this number, which is essentially the entropy, is the count of the number of degrees of freedom that are being excited. So quantum mechanics says that somehow the black hole should have some kind of structure of microscopic states which is not visible in the geometry. What are these bits? Now before going on, there's one more interesting thing. This particular formula for the number of bits is interesting because for most systems, the amount of information that they could store would be proportional to their volume. As you make the system larger, it would scale as the cube of the linear size, but this scales as the square, basically not as the volume, but as the surface area. In fact, it's rather precisely the surface area. When you consider the different kinds of black holes with different other quantum numbers, the amount of information storage is always exactly proportional to the area of this imaginary surface, the horizon, the point of no return. So this is the first place where the horizon plays a more, well, it still is immaterial, seemingly, but it still is playing a more direct role than you might have thought. And in particular, if somehow the basic information storage is related to its surface area, not its volume, it suggests that that fundamental degrees of freedom should be thought of as lying not in the volume, but somehow spread over the surface very densely, 1 per Planck length, which is this very small length that goes with the very small Planck time I told you about earlier. And it suggests further that the basic degrees of freedom when you unify quantum mechanics and gravity that are much less local than in any other physical system we've ever understood. Instead of being associated with points in space or smeared out points in space, they're somehow associated very non-locally with sort of the surface that surrounds the space that you're talking about. So this is a lot to infer from really a few very simple arguments about black holes. Now the information paradox, to introduce this, I need to talk about Hawking radiation. So here again is the black hole geometry. There's curvature. And in quantum mechanics, one is always producing virtual pairs, which normally appear and disappear essentially very quickly because of energy conservation. But in the presence of background fields, like the curvature of space, the pair can in fact become real and separate, where in this case one falls into the singularity and one escapes carrying energy away. And this is already a calculation that uses, again, both quantum mechanics, the virtual particles, and general relativity, but in a region where the curvatures are small, nothing very dramatic seems to be happening, where we still think we can trust the calculation. And of course, if this can happen once, it can happen many times, and so eventually the black hole emits all of its energy and disappears, and what's left, starting from a star or whatever, is simply outgoing photons. And now the claim is that the final state of the Hawking radiation is independent of the initial state, and it's also independent of anything you have done to the black hole, anything that you've thrown into it during the course of its evolution. I'll say a little bit more about that on the next slide. But this, if true, is where quantum mechanics has to be modified, because in quantum mechanics you always have some kind of Schrodinger-like evolution. This is true in quantum mechanics, it's true in quantum field theory, it's true as far as you know in string theory. In quantum mechanics you always have some kind of Schrodinger-like evolution which allows you to figure out the future state from the past state, but it works both ways. You can figure out the past state from the future state. It doesn't allow this kind of information loss. And rather, what Hawking said is that one needs a generalized form of evolution where a state, instead of simply evolving differentially into a new state, in the final, after the black hole is gone, there is not a unique quantum mechanical wave function. Rather, there is a large set of possible wave functions and some classical probability for each, which he very aptly summarized by saying God not only plays dice, referring to the uncertainty of quantum mechanics, but he sometimes throws the dice where they cannot be seen. That is, you not even knowing this additional uncertainty of not knowing what the wave function is. Now many people reacted badly to this, and for good reason, for principled reasons. So we might distinguish this situation from just burning a book. Burning a book clearly scrambles its information. It takes whatever was printed on the page and turns it into outgoing photons and whatever else. But it doesn't. But of course, Schrodinger's equation doesn't. The basic laws of quantum mechanics still hold. At a microscopic level, this entire process is describable by Schrodinger's equation. You can, the final state, though it is highly scrambled, is still a pure quantum mechanical state. And so the widespread assumption was that Hawking had simply not been careful. He had mistaken scrambling of information for actual loss of information, and a more careful calculation would fix this whole thing up. And for 20 years, people tried to do a more careful calculation and failed because, in fact, he was basically right, at least by the rules that everyone was playing with, because the difference between this situation and this situation is the existence of a horizon. Once you've got that horizon, once you've got any kind of information behind the horizon, there's no way it can escape. There is no way it can influence anything that happens later. To get the information out, it seems that one would have to effectively transport it faster than the speed of light. So these two intuitions, one saying, well, all thermal systems should be the same, even black holes, but black holes have horizons. There were other problems too. If you're going to start changing the evolution if you're going to change the quantum mechanical laws in exotic environments like black holes, well, of course, the laws of physics hold everywhere, and what can happen in a black hole can also happen at very short distances through virtual processes, and so Hawking's modification would be a radical modification, probably producing unacceptable effects like non-conservation of energy if you really tried to make a theory based on it. And so for 20 years, roughly, after Hawking's original argument, basically there are three broad classes of possibility: that Hawking is right and quantum mechanics is modified, that somehow the information gets out, and there's a third possibility, which is that maybe the black hole doesn't actually finish evaporating. It stops when it's very small, but then it's still, you need this small object which contains a large amount of information, and that creates problems of its own. And so certainly my own state of mind for 20 years was sort of going around in circles, trying to make one after the other of these work, failing and going on to the next one. And it was hard to see how this would ever be resolved, and remarkably, we now think we know what the truth is. So it was solved in a way that's partly direct and partly indirect. So many complicated quantum mechanical systems have been found to have a property known as duality, which is where you have what seem to be two very different quantum systems, but they're actually secretly the same, just being looked at in a different set of variables. Basically what you have is you have one quantum system, and it has two or more different classical limits. And so you think these are two different theories, you quantize the different classical limits, and you get the same quantum theory. And this is a surprising thing, but it's true all over the place. It's true in relatively simple low-dimensional quantum systems. It's been found to be true in a large swath of supersymmetric field theories, of grand unified field theories, and string theories. But Maldacena found something very striking. He found a system in which the two pictures, in one picture you had quantum gravity, this very puzzling theory with paradoxes that we're trying to understand. So in one picture you have a quantum mechanical black hole, and in the other picture you have a much more ordinary system, just a gas of strongly interacting particles, not so different from the quarks and gluons of the strong interaction. So there's a cartoon of his duality. And as with Maxwell, this was a tremendously unexpected connection between widely different areas of physics. This is the most cited paper in the history of high-energy physics. It's been that influential. It's in the 15 years since we have had this. It's just dominated the way we think about things. When you have two ways of thinking about a system, you learn a lot in both directions. In fact, they used to produce this state of matter over in Long Island, and many of its puzzling properties are best understood by thinking about it as its dual description as a black hole. But for the purpose of my talk, the real interest is that this is a system which, although it's complicated, we know a lot about it fundamentally, and so it tells us things about the quantum mechanics of black holes. In particular, since we know that quarks and gluons and particles described by quantum field theory obey ordinary quantum mechanics, information can't be lost. It provides the bits that Bekenstein-Hawking predicted, and it is holographic, because although this picture doesn't really display it, these bits actually live on the surface surrounding the black hole. And so it completes all of these inferences that have been made from the entropy puzzle, and moreover answers seemingly Hawking's question about the fate of quantum mechanics. And in fact, it was largely based on Maldacena's duality that Hawking conceded. And which is interesting, because you could choose easily to be a skeptic, because this duality is not proven. 9,000 papers have failed to find a mistake, but it's not proven. But he found this line of argument compelling. So why aren't we done? So okay, this holographic principle, this idea that physics is fundamentally non-local, is really new. We have no intuition for it from anything we've worked with before, and we'd like to understand it in detail, especially because Maldacena's duality actually works for gravity in a very special box, so-called anti-de Sitter space, and we'd like to understand quantum gravity in an expanding space-time. The killer application for a theory of quantum gravity is the initial conditions on the universe, how the universe began. The interior of a black hole is a lot like a Big Bang in reverse. It's crushing into a singularity instead of expanding from one, but like a black hole, there are horizons, points of no return in cosmology, and so understanding this would be a good place to start. And finally, where exactly did Hawking go wrong? How does the information get out? So again, there's these three alternatives, and the one that seems to be realized is in some ways the most conservative and in some ways the most radical. It's the most conservative because it says that that black holes are really very much the same as any other kind of thermal system. So kind of it points to a unity in physics. But it's the most radical because it seems to require, again, transfer of information faster than the speed of light. And again, this is not entirely surprising because of this holographic nature, this non-local nature of this duality, but we need to understand the details. Now, one of the nice things about Hawking's original argument was that it presented such a sharp set of alternatives, each of which had positive and negative features, that it was very hard to ignore. In fact, I'm really in awe of Hawking because, in his 1976 paper, he said he threw out this challenge. He said that quantum mechanics, isn't right. It has to be modified. And for at least 20 years, people looked at this and said, he must be wrong. I'm going to find his mistake, and they failed. Even though there were many subtleties in his argument, many subtleties in the system, he had in the very first paper really had understood things. He had foreseen these subtleties, so he threw out this challenge which one couldn't ignore. Now we think we at least know which of the alternatives is realized, and we have these somewhat fuzzier questions of trying to understand it better. So the news from the last year is in fact that we have what seems to be another paradox. You have another situation where not all the things that we believe to be true can be true, apparently. So what do we now believe? We believe, again, that information is not lost, thanks to Maldacena and others. But also we believe that, in fact, so information somehow has to get from the inside to the outside. But we expect that no single observer sees anything unusual. An observer who stays outside the black hole sees nothing unusual, nor does one who falls in. And in fact, they see different things. They see different things. Good. So in fact, I talked about a mechanical transport of information from the inside to the outside. But actually, somewhat before Maldacena, Tufte and Susskind had proposed something more elegant, which is that there is a new relativity principle. They called it black hole complementarity, which says that different observers perceive the information as being in different places, but there is no conflict because these two can't signal to each other. The observer inside can't send a signal out. The observer who's outside, as long as it's late enough, cannot send a signal back in. And so by all the thought, Lenny in particular, Susskind, argued by a series of thought experiments that this new relativity principle was perfectly consistent. And it also seems to fit very nicely with this duality of Maldacena, because in the duality of Maldacena, again, we have these two different pictures, the black hole and this gas of bits. And in one picture, the information sits in the black hole. In the other picture, the information sits in this gas of bits, which is somehow, surrounds the black hole, even at some great distance. So it all seems to fit together. But in fact, the new argument is that apparently, as far as, that these three assumptions are seemingly not, in fact, consistent with one another. Okay, these are my partners in crime. The basic argument is very short. I've even shortened it here because I wasn't sure of the audience, but even at worst, it fits on 2 slides. It's that those three postulates taken together require the system to be in an impossible quantum state. And one can focus on sort of 3 quantum bits. Again, so I've reverted now to my other way of drawing black holes. So A and B here are the Hawking pair, A inside and B outside. And C is some second Hawking photon. Actually, what it really is some kind of composite of a bunch of the other Hawking photons, but to make the picture simpler, I've pretended it's a single Hawking photon. And now, the Hawking process is a quantum process. There's an amplitude to produce a pair, so one inside and one outside, and the amplitude to produce no pair, and they're in some superposition. Conservation of information, however, requires that the sum of all the outgoing Hawking photons be a pure state. And that means that any given one of them, say again this photon B that's common to both pictures, this is again this is the late stage and the black hole is gone, the photons are all traveling away. Conservation of information requires that in fact any given Hawking photon be entangled with all the others, and in particular one could distill from the others a single bit of information with which it's entangled. So this is what you get by assuming that no observer sees anything funny, just applying local laws of physics. This is what you get from conservation of information. And again, these are not consistent. I've written here sort of a possible sets of possible wave functions, two possible wave functions for these three bits, A, B, and C. And again, sort of local physics at the horizon says that you produce A and B in a pure state, and then C would be doing whatever it does. Purity says that B and C have to be in a pure state, and then A does whatever it does. And you can make this more formal with strong subadditivity of the entropy, but it's easier to just try to make things work with 3 bits. And there is no wave function that has both properties. You have one wave function which would imply information loss if it were true, and you have another wave function which breaks the entanglement across the horizon. And what this implies, in fact, is that there is some kind of sharp wall of energy at what was supposed to be an immaterial sphere. And well, I make the analogy with breaking a chemical bond. It's not a real sharp analogy, but if you lose this entanglement between these two particles inside and out, it's like breaking a chemical bond. More precisely, whenever you have a quantum system with many degrees of freedom, nearby degrees of freedom have to be correlated. They have to be entangled. Because if they weren't, there would be some energy cost. They talk to each other, they interact, there's entanglement between them. If you don't have that, you've paid some large energy cost to get to a higher energy state. And in fact, so if you give up the entanglement between these two nearby quantum fields, you have a large energy density at the horizon, which my young colleague Don Marl named a firewall. And so this is the picture one gets, seemingly, if you try to preserve information. Again, all we've done is to run Hawking's argument backwards and try to be careful. This argument could have been made a long time ago. In some ways, we've been helped because people from quantum information theory have come into the subject, and although Hawking didn't need quantum information theory to find his paradox, but they certainly helped to make it sharper, to make us think more clearly about how quantum mechanics works in a context like this. Anyway, though, our argument would have made perfect sense to Hawking even in 1976, but he would have said then, well, of course, this doesn't happen because information is lost. Anyway, there is an observer. The observer, if this is true, the observer falls into the black hole, of course, sees something very dramatic. They see basically space-time end where it was supposed to be quite smooth. This is hard to believe, and certainly when we first found this, we didn't believe it. We spent some time trying to find our mistake and failing. We asked other people. Eventually, I called up Lenny Susskind, who's kind of the godfather of this subject, and I thought Lenny would tell me, "Oh, Joe, I thought about this 10 years ago, and the answer's in that paper over there," because he's done this to me before. But in this case, no, and so he had no answer. And so after a year, people were still confused. And as it seems, to summarize the situation, there are with the earlier puzzle, there were sort of 3 sharp alternatives. The subject hasn't yet quite congealed into a fixed number of sharp alternatives. There's more a long list of things that people are trying, but a remarkably large number of ideas are starting to loosen the rules of quantum mechanics. So this whole subject has been a battle between quantum mechanics and space-time. Hawking said quantum mechanics loses. Maldacena said no, space-time loses, but in a subtle way. The Firewall says no, it's not subtle. Space-time loses in a big way. The entire interior disappears. And maybe we've gone too far. Maybe in fact there is some again loosening of quantum mechanics. These are interesting ideas. A proposal that if you have a violation of quantum mechanics, but there is no quantum computation you can do to demonstrate it, then that's okay. It's not clear what that means in terms of the fundamental equations. An old idea that if you impose a boundary condition at the final state, at the black hole singularity, which is the future, you resolve all problems, except for causality, because what does it mean to impose a boundary condition in the future? An interesting idea that space-time comes from entanglement, that the Einstein-Rosen bridge, the wormhole that connects some black hole pairs, is in fact derived from, it gets its existence from the quantum correlations between the two black holes. A very interesting idea. If I had to bet on one, I would bet on this one at this point. That relaxes quantum mechanics by changing the rules for observables. But really, all of these at this point are frameworks, not theories. There is no theory. Even for the firewall, there is no dynamics. We don't know how if it forms. We don't know how it forms. We don't know when it forms. There's an old idea called the fuzzball. So string theory has, Andy mentioned these extended objects called branes. And we do know actually some situations where what looks like a space-time singularity puffs out into, in fact, a spherical shell that is non-singular that we understand. And for some time, Samir Mathur has been trying to make this work for the Schwarzschild black hole, of the black hole singularity. But the difference again is causality. It's that in those cases everything is causal. In this case, this would have to happen in effect faster than the speed of light. It's natural to ask, I've been talking about thought experiment black holes, which means that they're much more isolated than any astrophysical black hole, that we have the ability to observe them over longer time scales and greater precision than we can do with the astrophysical black hole. But still, when the hope, of course, is to learn something unexpected and striking, it's too early to say. It's quite possible that the exterior of the black hole is exactly as in the usual picture. Again, the goal is cosmology, where there are horizons also, but it's still too early to say. The main thing is that this whole thing is giving us a new lever on understanding the theory of quantum gravity. So coming back to, we've learned a lot from thought experiments. We learned about black hole bits, the holographic principle. Maldacena's duality was discovered in response to it. After, the thought experiment was one way to see that the equations were incomplete, but Maxwell also tried to make models of how the electric field, magnetic field were what they were, so this is his picture of space being filled with little wheels and gears. And this was his model of those fields. He actually had a very modern point of view. That is, he didn't take seriously the detailed pictures, but he was simply using them to derive the right equations. Anyway, in this whole subject, in both the firewall itself and in these various ideas that are alternatives, I feel that we're very much at this stage. Mainly, we're really just trying things which will look silly in the future to see what might work. And it certainly, I still worry that there is some trivial mistake, that there is some answer that will teach us nothing deep. But it seems, given the amount of confusion that this has led to over the last year and a half, this will lead us to a more complete understanding of quantum gravity. So, thank you.